In today's lesson, we are going to look at optimizing volume and surface area. So in the previous lesson, we talked about optimizing as being a way to kind of get the most out of something. And in case of the perimeter and area, or given a fixed perimeter, we're trying to get the most area. So we're going to be looking at trying to optimize volume and surface area. So just to start off, when we're trying to optimize volume and surface area, a cube is the shape or the three-dimensional object that gives the optimal dimensions for a box, meaning it gives us the most volume, while also minimizing the surface area. So if you can think of creating a package or package production, you probably want to create something or come up with measurements that give you the most volume or holds the most, while reducing the amount of materials required to make that object. So when we're looking at a cube and we're trying to maximize the volume, because we're dealing with a cube, when we look at the volume we know is length times width times height for a cube, and because it's a cube, all sides are going to be the same, so we could say side times side times side, or the volume of a cube is side cubed. So the same value multiplied by itself 3 times, because it's a cube, all the dimensions are the same. Now, in order to minimize the surface area, again, because we're dealing with a cube, actually let's put this in the middle. Because we're dealing with a cube, if we take a look at kind of the general formula for surface area of a cube, it's 2 times the length times the width, plus 2 times the width times the height, plus 2 times the length times the height. So again, because it's a cube, the length, the width, and the height are all the same values. So instead of being 2 times the length times the width, it would be 2 times, we could say s squared, because it would just be s times s. Same with the width and the height, same with the length and the width. We can simplify this then to 6 times s squared. So again, different ways we can look at it, but this is kind of a simplified version of our volume and surface area for a cube, which gives us again the maximum volume and the minimum surface area. So we're going to use this to help us come up with to answer some questions. So for example, a packaging company needs to design a box that will hold up to 125 cubic centimeters of material. What are the optimal dimensions for the box? And what amount of material will be needed to make the box? Well, again, because we know that it has to be a cube, all the dimensions need to be the same. So we can think about, well, how can I find out what those dimensions are? Well, we are given a piece of information. We are told what it needs to hold, or the volume it needs to have. So we know that the volume is equal to 125. So we can actually go through and plug this into our volume equation for a cube and help us find the individual side lengths. Again, volume is equal to, we said it was side cubed. In our case, we know the volume is 125, so 125 equals a value cubed. Now we have to think about solving. How do we solve for this missing value? Well, how do I cancel out cubing? What's the opposite of cubing something? In this case, the opposite of cubing something is doing the cubed root. So kind of how like the opposite of squaring something is the square root, the opposite of cubing something is the cubed root. So if we take the cubed root of 125, we will get our side length. And in this case, it is 5 which is equal to the side length. So we now know that our measurements for our cube are going to be 5 by 5 by 5. We can then use this to help come up with our question, or answer our question. In this case, we're looking for what amount of material would be needed to make the box. So this is the surface area. So now I can go through and find the surface area given the side length measurement. Again, the shortened form for our surface area is 6 times s squared. So in this case, 6 times 5 squared. I get 150 centimeters squared. So therefore, if I wanted to come up with a box that holds the most or has the largest volume, or sorry, not the largest volume, it has a volume of 125. We want to come up with the optimal measurements. So in this case, the measurements would be 5 by 5 by 5. Then using that, the amount of materials needed would be 150 centimeters squared. If we look at the second example, so in this example, a company packages basketballs in a cube-shaped box. The company plans to use 500 inches squared of material. What is the largest diameter of the ball that will fit the box? So, again, it talks about we're dealing with a cube. We're given how much material, and we're trying to come up with what is the largest diameter, or basically the dimensions. We're trying to come up with the dimensions of the ball, or of the box. So if I imagine I have a cube here. So I have a cube, and I place my basketball. Try to imagine a basketball. Nice little rough drawing here. So I have my basketball inside that box. If I'm looking for the diameter of the basketball is actually the same as the measurements of our box. So the diameter in this case would equal the side length of our box. So if we can find the side length, we can find the diameter of the ball. Well, where do we start? Well, what information are we given? We are given the surface area because we're given the amount of material needed. So if we're given the surface area, chances are we have to use that surface area formula and rearrange it. So the surface area formula again was 6s squared. I can replace the surface area with 500. So 500 equals 6s squared. And now you can go about trying to solve the equation. If I want to get rid of the get the s squared by itself, I first need to get rid of the 6. So I'm going to divide this side by 6, divide the other side by 6. One side cancels out. We're left with 83.3, which is equal to, not x, s squared. How do we cancel out the s squared? Well, if we're trying to cancel out the s squared, in this case then, similar to the last example, we need to take the square root this time. So I take the square root of both sides. One side will cancel out, and we're left with 9.1 equals s. So now we have the dimensions of the box, and therefore the dimensions or the diameter of the basketball. So therefore, the largest ball that would fit can have a diameter of 9.1 inches. So you can have a ball with a diameter of 9.1 inches. That's the largest ball that you could fit into these boxes, given the material. Next, we're going to look at optimal dimensions for a cylinder. So if you can imagine, what type of cylinder would we need that would have optimal dimensions? Well, it's kind of already given to us, right? It says when the height and the diameter are equal. So if we can imagine, that's very similar to a cube, right? If I have a cylinder and the height and the diameter are the same, that's essentially saying we have a cylinder that would fit into a cube. Right? So that's where we kind of get the same, or that's why we get this idea, where we come up with this requirement to get the optimal values. So because we're dealing with this, height would equal diameter, and you might also say the height is equal to 2r, or 2 times the radius. We're going to use this in a similar method to kind of come up with a simplified formula, specifically for when we're trying to optimize, because we're optimizing based off of these given characteristics. So the volume of a cylinder is equal to pi r squared h. What we can do is we can replace h with 2r, and then we can simplify this to 2 times pi times r cubed. So that is our formula when we're trying to deal with optimization in cylinders when looking at volume. For the minimum surface area, we're going to do the similar thing. We're going to write out the surface area formula, 2 pi r squared plus 2 pi r h, and everywhere we see the h, we're going to replace it with 2r, just so we have a consistent or one variable, because we can break it down into all one type of measurement, or using only one measurement. So 2 pi r squared plus 2 pi r times 2r. So all we're doing is we're using this to substitute in. We then get 2 pi r squared plus 4 pi r squared. And when we combine this, we get 6 pi r squared. So this is our simplified version of the surface area when we're trying to come up with optimal values. And hopefully you can kind of see a connection between this and the cube version, right? Because the cube version was 6s squared. So very similar, except we have the pi in there because obviously we're dealing with a cylinder and not a cube. So we're going to use these these final simplified formulas in a similar way as we did in the previous example, because again, we're trying to figure out, we're trying to basically solve for what the dimensions would be given a certain amount of either material or space. So, for example, a pop company fills its cans with 355 milliliters of pop. What are the best possible dimensions to use so they can minimize the amount of material they need? Right, so again, we're trying to optimize this to find the minimum amount of material given the volume that it has. There's one thing to add, just a quick kind of unit conversion. 1 milliliter equals 1 cubic centimeter. So this 350 milliliters actually means that we have 355 cubic centimeters of volume. So what we're going to do is we're going to go through a similar way that we did in our previous examples, right? When we were looking at the cubes. We're going to start off with what we're given. Well, we are given the volume. We know the volume is 355. Because we're given the volume, we're going to have to use the volume formula to help us come up with our dimensions. So in this case, the volume formula, V equals 2 pi r cubed. Right, that was the volume formula that we just found on the previous page, or the previous slide. Now we're going to substitute in the information that was given to us, which is that volume. 355 equals 2 pi r cubed. If I want to get r cubed by itself now, because again, that's the goal, to solve for r, I can get rid of this 2 pi by dividing by 2 pi. And I can do the same thing to the other side. One side will cancel out, and we're left with 56.5 equals r cubed. Now we're at a similar place to the last one. How do I get r by itself? Well, I need to square root or cube root 56.5. That will cancel out the r cubed. I'm left with then 3.8 is equal to r. So we now know that our radius for our pop can to have the minimum amount of material has to be 3.8. Let's take a look at what the diameter would be, right? Just again to get a better sense, right? We know that the diameter is 2 times the radius. So 2 times 3.8 gives us 7.6. So we know the diameter is 7.6 centimeters. And because this is the optimal shape, right, because we're looking at the minimum amount of material, we know that then the height has to equal the diameter, which we just found was 7.6 centimeters. So in order for a pop company to minimize the amount of material they need for their pop cans, given that each can holds 355 cubic centimeters, the height and the diameter should be 7.6 centimeters. So take a look at a pop can the next time and see if that measurement is true. Does a pop can fit the optimal dimensions to minimize the amount of material? If not, why? Why do you think pop companies, why don't they use the optimal dimensions to minimize the amount of material they need? Right? Think there's no right or wrong answer. Well, there might be a specific answer to that, but again, we're not going to focus too much on that. But that's just something to think about. Why would companies not use dimensions that give the minimum amount of material to make the product? Looking at number 2, a milk company would like to start selling their product in cylindrical containers. If they can afford to use 675 centimeters squared of material, what volume of milk can the package hold? So this is kind of the other direction. We're given the surface area because we're given how much material they can use. So maybe they've done kind of a cost efficiency, or I don't know, a cost report, and they've determined that they can spend that much on material per container. So how much volume could they have? Well, we're going to start with what we're given. In this case, we are given the surface area. So because we're given the surface area, that's where we're going to start. We're going to start with the surface area. We're going to use the formula, and we're going to find the dimensions. Once we then find the dimensions, we can go back and then plug the dimension or the value into the other formula to calculate the volume. So again, that's kind of how it's always going to work when we're dealing with these types of optimizations. Given the information, we use that formula to find the dimensions, and if we need to find then the other information, so whether if we're given surface area, do we need to find volume? If we're given volume, do you need to find surface area? Once you find the dimensions, you should be able to do that. So we start off with our surface area formula that we determined in this lesson. We're going to plug in the surface area that we're given in the question. We're going to solve and try to get r squared by itself. Divide one side by 6 pi, divide the other side by 6 pi. One side cancels out. We get 35.8 equals r squared. To cancel out the squared, we square root. And we're left with a radius of 5.9. So we know that in this optimal cylindrical container, the radius would have to be 5.9. I don't care too much about the other dimensions because the question really isn't asking for that. What the question is now asking for is what volume could the container hold. So we're going to then go to our volume formula that we determined, plug in the optimal radius, 2 times pi times 5.9 cubed, and now we can go through and solve for the optimal volume. So 1290.4, it would be centimeters cubed, but from the previous question, we know that 1 centimeter cubed is equal to 1 milliliter. So this is the same thing as saying 120 or 1290.4 milliliters. So therefore, given this amount of surface area, the optimal or the most volume that our container would hold would be 1290.4 milliliters. So again, the main thing from this lesson is understanding that if we want to optimize a prism or a cylinder, there are some specific dimensions. Let's scroll back quickly and look. If we're trying to optimize a prism, chances are we're going to be using a cube. Based off of that, we have a kind of generic formula now, because what's unique about a cube is that all the sides are the same. So we have a specific formula now for the volume and for the surface area. So we can use that to help us determine if we're given one piece of information to find the other, or if we're given one measurement like surface area or volume, can we find what the optimal dimensions are. The same thing applies to the cylinder. It kind of matches that idea. The cylinder takes on a dimension similar to a cube. The diameter and the height are equal, so based off of that we can then come up with these generic formulas specific to optimization, because those side lengths or those dimensions would be the same. And we can use it in the same way. If we're given one measurement, so if we're given volume, we can then find the optimal dimensions, which we can then use to find the surface area, and vice versa. Given the surface area, we can use the formulas to find the optimal dimensions and then find the volume if needed. And so again, it's all about optimizing, coming up with the most or the best, right? Or in this case, the most volume or the minimum surface area.